Okay. Hello, everyone. I just wanted to finish up the example so we can work on the proofs on Monday. And we left off here in class. And so we talked about the kernel there being the identity, being every function f of x equals k, where k is any constant, and then the identity element is the f of x equals 0 function. You can also show that phi from G to G given by phi of f plus G equals the integral of f plus G dx. You can show that that's a homomorphism. You can also show that phi from G to the positive reals given by phi of f plus G equals the definite integral from 0 to 1 of f plus G dx. All right, so you can also show that that is a homomorphism as well. Okay. We also can look at this for linear algebra. Okay, so we have in linear algebra, we can let A be a m by n matrix, and we define phi from Rn. Okay, so that's an n-dimensional vector space to Rm, given by phi of some vector v, which is in Rn, it equals a times v vector. Okay, and so from linear algebra, you may remember this is what we denote as a matrix transformation. And to prove that this is homomorphic, or that it's homomorphic, we can take, again, the same rules apply. Take two vectors in our domain. Well, in this case, we're going to be taking vectors, but take two elements in our domain. And we could say u plus vector v equals a times u vector times the quantity vector u plus vector v. All right, and you can multiply, remembering linear algebra, and that's going to equal phi of u vector u plus phi of vector v. Okay. If you want it, you can also try to determine and figure out what's the kernel of this group. Okay, so that's A. So I want you to think about what's the kernel of phi. Okay. B, GLN, which is a group of invertible n by n matrices under multiplication, and it's being mapped to R star under multiplication, which is all the reals except for 0, right? And it's given by phi of AB equals determinant of AB. So again, to prove this, two elements. So we're taking two matrices in our domain, and phi of A times B equals determinant of A times B, which you should remember, since these are, in general, is equal to the determinant of A times the determinant of B, and that's phi of A times phi of B. Again, I want you to think about what will the kernel of phi be. Okay, I want you to see if you can figure out what would the kernel be. On Monday, we're going to do proofs, and you'll see, okay, if our function is a certain way or it has certain characteristics, then it will, the kernel will be this. Okay, we'll talk more about that. Let's look at number 5. So S sub n, we know that group is a symmetric group, right, on n letters. And we're going from S sub n to Z2. And the way that we're defining this function is that for some alpha in Sn, it's 0 if alpha is an even permutation, and it's 1 if alpha is an odd permutation. And we want to show that this is a homomorphism. So again, I won't use yellow, but again, we want to show that phi of, let's say we take two elements, let's say sigma and mu equals, okay, phi of sigma plus phi of mu, because we are going under, Z2 is under addition, right? So phi of mu. Okay. Okay. So we actually need to consider, to solve this, we have to consider 4 cases. Okay. And those cases are, well, 1, if sigma and mu are both even permutations, right? 2, if sigma and mu are both odd. 3, if sigma is even and mu is odd. And then 4, if sigma is odd and mu is even. All right. So although we need to consider these 4 cases, we really only need to show 3, right? We'll show when they're both even, when they're both odd. But 3 and 4, you can do WLOG, right? So you can say for 3 or 4, this is going to be without loss of generality, which means no matter which one you prove, it's going to follow the same structure. You're not losing any type of specifics if you don't prove one versus the other, okay? And so let's look at, so taking case 1, so assume both sigma and mu are even. Well, what does that mean? So sigma, mu, and you may have to go back and revisit permutations. But if sigma and mu are both even, then when you compose it, it will also be even. And so this will equal 0, okay? Which is the same as phi of sigma plus phi of mu, right? Or another way, I think a better way to write this is it equals 0, which is the same as 0 plus 0, which is phi of sigma plus phi of mu. Okay. And what about if they both are odd? Okay. So if they're both odd, what happens? So case 2, assume sigma and mu are both odd. Both odd. Okay. Okay. Well, again, if we have two odd permutations, if we're composing two odd permutations, then we're going to get out of even, right? So we're going to get back out 0. Now here we have to be a little careful, because note that phi of sigma plus phi of mu is going to be 1 plus 1, which equals 2, but in Z2 that equals 0. Thus, phi of sigma mu is equal to phi of sigma plus phi of mu. Okay. So again, if you have to go back over making sure you get, when you compose two even permutations, you get an even. When you compose two odd permutations, you get an even as well. Okay. It's very similar to thinking about adding even and odd numbers, right? Because it's an even number of transpositions and things of that nature, right? So it goes back to that. So if you want to think about it in that sort of simplicity of, well, if I'm composing two even permutations, that's the same as if I'm adding two even numbers. And if I'm adding, composing two odd permutations, that's the same as adding two odd numbers. I'm going to end up with an odd permutation. I'm going to end up with an even permutation. Okay. And then let's look at case 3 without loss of generality. So we won't have to look at case 4. So that which one was case 3? Sigma is even. Okay, let sigma be, I'm just going to say be even. We already know that means permutation. And let mu be odd, right? And so phi of sigma mu now is going to be odd, right? So it's going to equal 1. And this is the same as 0 plus 1, which is the same as phi of sigma plus phi of mu. Okay, you can look at it like that. Or you can do it separately like we did that last one. Okay, so therefore, it is an even, therefore it is a homomorphism. Phi is a homomorphism. And you can also, so therefore it's a homomorphism. So you can think about it in terms of how would the kernel look here? Okay, so think about the kernel for that one as well. Okay, something else we can look at again, just give you more examples in terms of our homomorphism. Let R be a fixed integer. Define phi sub R going from Z to Z as given by phi sub R of n equals Rn. Okay, and again, if we want to prove that this is a homomorphism, take two elements, let A and B belong to Z. So phi sub R of A plus B equals R times A plus B. We have the commutative property, and so that equals phi of A plus phi of B. Okay. What's the kernel? Okay. Let's see. So I want you to see if you can determine the kernel for these examples. I believe this is our last example. Yes. So we're going from Z. Phi is going from Z under addition to Z sub n under addition mod n, given by phi of m equals R, where R is the remainder when m is divided by n. Okay. And so to prove that this is a homomorphism, let X and Y belong to Z under addition. So phi of X plus Y equals X plus Y sub n. Okay. And that is going to be phi X sub n plus Y sub n, right? Because we're in mod n. And this is the same as phi of X plus phi of Y. Okay. And again, I want you to tell me the kernel. Now here, let's look at an example because I want to make sure you all agree with that format and that proof. So let's just do a check. That's too light. Let's do a check. So let's say we under Z5, right? And let X equals 3 and Y equals 5. So phi of 3 plus 5, which equals phi of 8, is 8 under mod 5. Well, that's the same as 3 under mod 5, right? And then also phi of 3 plus phi of 5. Let's see if we're going to get the same out. That's 3 mod 5 plus 5 mod 5. And you know this will go to 0, right? So that gives us 3 under mod 5. Another example, X is 17, Y is 20. So phi of 17 plus 20 equals phi of 37, which is 2 under, we're still under mod 5. And so phi of 17 plus phi of 20, right, will give us 2 plus 0. Okay. And so we'll get the same thing. Okay. So I just wanted to give you some examples, and quickly, if you want a quick non-example of a homomorphism, I guess you can call this example 8, then you can let F go from Z to Z and let F of X be some constant, let's say 5. Okay. And you can easily check to see that that's not homomorphic. Okay. All right. We are done. I will see you to continue the proofs in class on Monday.